photo. So at the terrace on the 3rd floor, but I think we can meet here at the door and then all go all together. So remember 4:30. Okay, so I think many mathematicians worked on the problem of the representation of integer as a sum of 2 or 3 primes, at least since the famous exchange of letters between Goldbach and Euler, I think 1742.
Thank you for stealing my first slide.
And yes, I think you will give a lot of details about this, but since the work of Vinogradov in 1937, it was a challenge for many people to try to get the full Goldbac ternary conjecture. And this is the work achieved by just a few months ago by Harald. So I am very glad to introduce your talk on ternary Goldbac problem. So Harald Helfgott is working at CNRS at the École Normale Supérieure in Paris. Thank you.
Thank you. Well, so, all right. So what is the ternary Goldbac problem? So Goldbach, as most of you know, was an amateur, but also some sort of patron for Euler. He was older and had better political connections, and Euler needed somebody to write to as well. Euler was feeling a bit isolated in St. Petersburg, and he liked to write letters a lot. So the volume of the correspondence is really apparently a thick volume, though I have never seen it. But Goldbach really liked mathematics, and he was asking questions of Euler that were sometimes naive, but that were sometimes rather meaningful. And over time, the following question has come to be seen as one of the latter kind. So Goldbach asked a question that has now been split into two. So there's a ternary Goldbach conjecture, which states that every odd number is the sum of 3 primes, and the even Goldbach conjecture that states that every even number is the sum of 2 primes. Binary and ternary are terms that need no explanation. Of course, strong comes from the fact that the binary conjecture implies the ternary conjecture. Because if somebody gives you an odd number, n, and you already know the binary or strong conjecture, you just apply to n minus 3. So if n minus 3 is p1 plus p2, n is 3 plus p1 plus p2. Very well. So that's Euler. That's the letter, half in German, half in Latin, that Goldbach wrote to Euler, containing the statements of both conjectures, essentially. I couldn't find a picture of Goldbach, or rather, it's very easy to find one on the internet, and then if you look a bit harder, you will find a page explaining that that picture is not a picture of Goldbach. All right, so Vinogradov was mentioned, but I would really like to start the story with Harding Littlewood's work. I should say, in the 19th century, the only things that happened were that the conjectures became better known. In fact, the ternary conjecture was made again by Waring in the late 18th century. And also, the binary conjecture, at least, was verified by hand up to 2 million. But there were no results known beyond 2 million, or beyond the finite number. So Harding Littlewood's result was rather impressive. It was they who proved that every odd number greater than a certain constant c can be expressed as a sum of 3 primes, assuming the generalized Riemann hypothesis. And then Vinogradov showed, and that was a great achievement, that you don't need the generalized Riemann hypothesis. And Vinogradov's proof was extremely complex at the time. It has been simplified a bit since then. More about it in a second. So, well, here's the fantastic duo, and here's Vinogradov looking much older than in 37. But in 37, he was already bald. So the news are that, well, so I have managed to prove this for all odd numbers, whereas it was known only for extremely large ones and rather small ones. All right. So a bit on slightly lateral results, what do we know? Schnirelman had proven that every integer is the sum of at most k primes, where k now wasn't specified. K was specified and improved slowly. And then, well, Schnirelman's method is really what we would now call additive combinatorics. But then going back to Vinogradov's method and using doing many improvements, Ramere managed to show that every even number is the sum of at most 6 primes. And tau, this happened already when had been working on the problem for a while, tau showed that every odd number is the sum of at most 5 primes. And it's also known, the ternary Goldbac conjecture in its full strength was also known under the assumption of the generalized Riemann hypothesis. So it's really Zinoviev mostly, and I would say that none of the other three would be annoyed if I said that. Zinoviev showed that it was true starting, assuming GRH, that it was true starting at 10 to the 30 something, and then once you have that, getting up to that point, even though people hadn't literally got to that point, getting up to a lower point and then using some interesting arguments, that was quite doable, and it was done. All right, so what were the values of C? So Vinogradov did not specify at C. In fact, if you just open a book on analytic number theory, you will usually find an ineffective proof. That means a proof that does not just not give a C, but in fact the proof gives you no way to figure out a C because of the Siegel zeros phenomenon. Now, at least in Vinogradov's second version of his proof, or later versions, including the version in his book on the subject, he did give effective proofs. Maybe in the case of his first proof, it's not completely clear to me, but in later proofs, he did manage to avoid the Siegel zero phenomenon. And then, much later, a former student and assistant of Vinogradov, Vorodskin, managed to specify a C. It's a very large number, written very compactly, 3 to the 3 to the 15. And then that value of C was improved several times. The best value known was 2 with 1,346 zeros. Of course, this number, while much smaller than 3 to the 3 to the 15, is still beyond astronomical. What do I mean by beyond astronomical? One can be quite precise about that. 10 to the 80 is barely an astronomical number because the number of subatomic particles in the universe is 10 to the 80. Multiply that by the number of seconds since the Big Bang, and you will get that 10 to 100 is possibly the largest astronomical number. Beyond that, we can no longer speak of astronomical numbers. All right, so how far had people got with their verification? So the binary conjecture has been verified by computer up to 4 times 10 to the 18th. And using that, it's not very hard. It takes a medium-sized computation to check it up to 8 times 10 to the 30. Now, there's nothing special about that number. We could have left the computer in the basement run for longer. And in your home computer, you can probably do it up to 10 to the 28th or so, because all you have to do is construct a ladder of primes separated by no more than 4 times 10 to the 18th. And once the ladder goes past 8 times 10 to the 30, you have shown the ternary Goldbac conjecture up to 8 times 10 to the 30. Because if somebody gives you a number up to 8 times 10 to the 30, all you have to do is find a rung in the ladder immediately before your number. That rung is a prime, you subtract it from your number, you get a number smaller than 4 times 10 to the 18th, which must hence be a sum P2 plus P3. So your number, your original number, is P plus P2 plus P3. So it's the same trick as when you subtract 3, only barely more sophisticated. All right, so there's a bit of a problem though. It's that 10 to the 30 is quite a lot smaller than 10 to 1,346. If you get bigger computers, maybe you can go up to 10 to the 32 or 33, but there's no way you can, even the Pentagon cannot go further than 10 to the 34 or 10 to the 35, I think. So it's clear that computers are not going to solve the problem. The only way to do things is to improve the mathematical part. That was clear from the start. So it was clear that one needed to reduce C to about 10 to the 30. So I have reduced it to 10 to the 29, and that solves the problem. So the issue is, of course, how to bring it down to 10 to the 29 or thereabout. All right. So let me get back to what Harald Littlewood did. So what Harald and Littlewood were doing was just Fourier analysis over R mod Z. That's why it's called the circle method, because R mod Z gets called the circle. No? So you have this series where 8 of t is a weight function. You can choose a smooth weight, as Harald and Littlewood did. And then, just as when with the fall of the Roman Empire, concrete was forgotten, smooth weights were forgotten by number theorists for a long while, until about a generation ago, I would say. I think that's about fair. People in other fields remember that you must smooth, but people in number theory forgot for the most part. Vinogradov had his reasons for using just a very simple weight, but that makes the analytical part very hard, as we will see later, though it makes the combinatorial part easier. Then lambda of n is just a von Mangold function, so it's essentially the characteristic function of the primes. And E of alpha is just a complex exponential, which traverses a circle. So this just, I mean, S of alpha, you can just see it as the Fourier transform of f, where f is just the von Mangold function times the weight. That's it. All right. So the crucial identity is that you can express this sum as an integral. And this, again, you can see it abstractly very easily. It's just the fact that when you have a convolution and you take the Fourier transform, so S of alpha is just the Fourier transform of f, where f is lambda n. It's just that, as he said. So the transform of a convolution is just a product of the transforms. So I'm just saying here that the triple transform is indeed product. And why would we ever care about the triple convolution, which is then given in this way? Yes. Why do we care about this? We care about this because the triple convolution evaluated at n gives you the number of ways, the weighted number of ways of expressing n as a sum of 3 numbers where lambda does not vanish. That is, the number of ways of expressing n as a sum of 3 primes. Of course, there are also prime powers, but those give a tiny contribution because squares are very rare. So we want to show that the sum is non-zero, because if the sum is non-zero and not tiny, this will show that n can be written as a sum of 3 primes, in fact, in many ways. That's our goal. But that sum is equal to the integral, so we must show that the integral is greater than 0. So the circle method, as I said, is just Fourier analysis over R mod Z, and it's applicable to additive problems because the convolution behaves so very nicely under the Fourier transform. And the convolution gives you really an additive problem. It's an additive convolution. Very well. So how do we evaluate this integral? We partition R mod Z into intervals, into arcs. There are the major arcs and there are the minor arcs. The major arcs are not particularly big. They are major because they give the major contribution. You could call them the main arcs if you wished. So it's like this. The arcs, the major arcs are going to be the arcs around the rationals with small denominator. Small means less than m of x. We will speak more about m of x in a second. So up to now, m of x has been a power of log, but for us, m of x, for reasons that will become clear soon, will in fact have to be a constant. So the plan then is to estimate, that is, give a pretty accurate estimate, an upper and a lower bound for the integral over the major arcs, and then give an upper bound for the integral over the minor arcs. If you show that your integral over the minor arcs is at most in absolute value, no, it's less in absolute value than the value of your integral over the major arcs, you will have shown that their sum is positive, which is what we want to show. So strictly speaking, we just need a lower bound on the major arcs, but in practice, we give a pretty accurate estimate on the major arcs. It happens that way. By the way, yes, I will say that a bit later, but it is at this point in the strategy and not earlier that the method breaks down for the binary Goldbac problem. It's because in the binary Goldbac problem, the contribution from the minor arcs isn't really minor, it's the main thing. But we don't know how to bound the S of alpha from below on the minor arcs. All right, so in the major arcs, we can actually give asymptotic estimates. So how do we do that sort of thing? We do that by studying L functions. An L function is just given by a series, most of you know it. And what happens is you use this series defined in terms of characters modulo q, because you want to express as eta alpha x, your series, as a linear combination of series that involve chi. Well, why would you want to make your life complicated introducing a chi? It's that your angle is no longer alpha, as it was before. Alpha is a over q plus something small, delta over x. The angle is just delta over x, which is very small. Because as we will later see, delta is very small. In fact, for us, delta will be bounded by a constant. So this means that this sum will just be going, the phase will be going around a bounded number of times. And that makes it much easier to estimate. Very well. How do you estimate it? You use it as so-called explicit formula. So the term within brackets appears only when chi is essentially the trivial character. Rho runs over all non-trivial zeros of the L function. So you have your L function. It's defined on the complex plane. It doesn't vanish to the right of s equals 1. Here it doesn't vanish. Here it has some zeros on the real line, and you know where they are, so they are called the trivial zeros. But here, all the interesting or non-trivial zeros lie in this strip between 0 and 1. So rho runs over all those zeros, and f delta is a Mellin transform of eta of t, the weight times the phase, e delta t. So the Mellin transform is defined that way. As you can recognize, the Mellin transform is essentially a Laplace transform, which is essentially a Fourier transform. It's just a matter of changing variables. No? So it's a Laplace transform with a change of variables, and then a Laplace transform, if you take it on a line parallel to the y-axis, is just a Fourier transform. Very well. So what about this? Where are these zeros? So we want to know what f delta of rho is, and we also want to know where the rhos are. So what we believe, what everybody believes, is that all the zeros, all these interesting zeros, lie in fact on the so-called critical line, the line down the middle of the critical strip. This is precisely the generalized Riemann hypothesis. So this is believed but not known. All right, so what do we know? We know two kinds of partial results towards the generalized Riemann hypothesis. We know what's called zero-free regions. Zero-free regions, that means that there is a small forbidden region in which it's known that there are no zeros. So it's very narrow. It's a bit broader. It's a bit broader here, closer to the x-axis. But then it's very narrow. And here the evil Siegel zero might live. So there might even be an evil zero here in general. It looks like this. I would exaggerate it if I said it's like an hourglass, but it's a bit like an hourglass. It's just that even at the middle, it's not that narrow. All right, so people do know what C is, but so you can give a C that is just one digit. Whether it's 7 or 5, it depends on which papers have been finished or haven't been finished. But the point is that unfortunately, these zero-free regions aren't strong enough if we are going to prove the 3' problem. And there are regions that are broader asymptotically, but that are worse in practice than this one. The other kind of partial result that we know is of the following kind. For a specific chi, for a given L, and given also a constant h0, or t0, we can verify the generalized Riemann hypothesis up to that height, meaning up to, for imaginary numbers up to height t0, we ask a computer or ask ourselves, if we are masochists, to verify that all zeros up to t0 lie in fact on the critical line. But above that, we don't know anything more than before. The computations are finite, so it can be carried out only up to a finite height for a finite number of characters. By the way, the first person to do such a computation was Riemann himself. He did not give it as one of his public reasons for believing in his conjecture, but he did compute the first few zeros of the Riemann zeta function and did verify that they all lie on the line. And you can actually show that they lie exactly on the line by figuring out sign changes. And you can also count fairly easily how many zeros there are up to a certain point. Very well. So how far has Riemann's verification been taken? Very far up. How far up, or at least for the Riemann zeta function, how far up depends on whom you believe. Just to give an idea of different standards of rigor. So many people don't consider the Gordon-de Michel computation to be a proof. The Vedadivsky proof is generally considered to be quite strict, but perhaps not up to the very highest standards because it does not use what's called interval arithmetic. Nowadays, if you want to give a rigorous computation and you also don't want an enormous verification that will convince only people who will read it, then really the most practical thing is to use so-called interval arithmetic. And that's what Platt did. So Platt used interval arithmetic. What is interval arithmetic? Well, it's being honest with the computer. The computer cannot deal with irrational numbers ever in practice. It can deal with rational numbers, but it's really happiest computing with rational numbers whose denominators are powers of 2. So what you should really ask the computer is not, computer, please tell me what is the sign of pi over 2, unless you're proceeding symbolically, of course. You should ask, computer, I have an interval here, a comma b. A and b are the numbers of the form you love, denominator a power of 2. Can you please give me an interval in which sign of the interval a comma b is contained? And the computer says, yes, here I give you an interval c comma d containing the image of a comma b under the map sign. And because I'm very nice as a computer, I've tried to make the interval c comma d rather small. But all I guarantee to you is that the interval contains the image. So all your computations, or your floating point computations, you do that way. And if you do them that way, and then with modern computers that check whether a random neutrino has fallen on them and so on, by checksums, then it's all fine. So year H, that is the Riemann hypothesis for L functions, has been verified, or had already been verified by Platt in his thesis up to 10 to the 5. This doesn't seem like a lot, except that then you realize that there are almost Q conductors of modulus Q. So this is really, well, not quite 10 to the 10 characters, but about 10 to the 9 characters. And it's checked up to a height that is inversely proportional to T. Very well. So I got Platt some more computer time, and he checked it up to 2 times 10 to the 5 and 4 times 10 to the 5. That its pair should be even, excuse me. I first gave this talk in French. Here also the fact that you go further for Q even is just an artifact of what I needed. So this computation is to some extent tailored to my proof, but to some extent not, in the sense that this actually goes much further than what I actually ended up needing. And it's also computation of general utility, of course. You can use it for, it's not copyrighted, you can use it for whatever you want. Very well. It's not ad hoc for the ternary Goldbac problem. It's up to a point where I needed it, but it's of general utility. So how do you use such a verification? Well, you have to estimate that sum, right? The number of zeros, as I was saying, is easy to estimate. So the problem is that up to t0, all the x to the rows have modulus x to the 1/2. That is, the contribution of all the zeros up to the height where you have verified the Riemann hypothesis is very small because each term is of size square root of x. So that's very nice. But what about the contribution of all the terms with imaginary part greater than t? Then the contribution of x to the row could be as large as x. Remember that all you have beyond t0 is the zero-free region, and that's useless in practice, in fact. So all you can do is get, all your hopes are centered on f delta of rho. You want f delta to be such that f delta of rho is very small for when the imaginary part of rho is large. And it decays rapidly as well. So once you get there. So what will you choose as eta? Because really, f delta of rho depends on eta only, and delta. So Harald and Littlewood used e to the minus t, and for that the Mellin transform is of this form. It looks rather nice. It's a nice closed form. And then how does it decay? It actually decays pretty well. It decays exponentially. So in fact, well, Harald and Littlewood were very clever people. There's only a little problem here in that t over 2 pi delta is actually not that large. We will actually have to verify if t0 will be proportional to delta. So our computation, so it will actually be, this means that if delta can be as large as, say, 100,000, and you want to verify your hypothesis only up to 5 million, say, then all you will be able to say about t over 2 pi delta is that it's larger than 8 or so. So the exponent there in that exponential is about 8, unless you want your computation to be huge. So e to the minus 8 is not that small. E to the minus t is very small, e to the minus, because t will always be at least 200, say. E to the minus 200 is negligible, but e to the minus 8 is not that small, and you're going to be multiplying it with other terms, so that's no good. So what can you do? So what was really, in my view, the motivation for Hardy Littlewood's choice? So these were first-rate analysts, and Hardy himself was extremely familiar. In fact, he was responsible for one of the forms of the uncertainty principle. So the uncertainty principle, most people know it as a principle in physics, but really the principle in physics is just an application of the principle in mathematics, which tells you that a function and its transform cannot both decay very fast. In this weaker form, the principle would be that you cannot have a compactly supported function whose transform is also compactly supported. That would correspond to determining exactly the position of a particle and its velocity, say. But more generally, in the case of the Mellin transform, it means that you cannot have a function that decays faster than exponentially and whose transform also decays faster than exponentially. And why do we care about that? Well, to make a long story short, what happens is that the Mellin transform, f delta, decays like the transform f0, that is the Mellin transform. We're studying the Mellin transform f delta of eta e delta x of t. Now the issue is that f delta is about f0, that is, it's about the Mellin transform of eta, if you wish, once it's rescaled, for delta close to 0. But for delta away from 0, f delta is actually closer to the function eta itself. So to ask f delta to decay rapidly both for delta small and for delta large is the same as asking for the Mellin transform of eta to decay rapidly and for eta itself to decay rapidly. So you could say that the option that Hardy Littlewood's choice is optimal because it decays exponentially, but the function decays exponentially and its Mellin transform decays exponentially. However, nobody's telling you that you cannot have a function that decays faster than exponentially and whose Mellin transform also decays exponentially. And that's the case, for example, for the Gaussian. So the Gaussian has faster than exponential decay and its Mellin transform still decays exponentially. just a bit slower than before. But we don't care, because pi over 4 times t is still huge. Yes, the exponent is huge. E to the minus huge is small. So I use this Gaussian. So what is the Mellin transform then? It's a bit less explicit than before, but at least it has a name that's comforting. It's a parabolic cylinder function. This has been much studied by physicists and engineers, at least for real parameters. Now we need it for complex parameters. And then it has been studied, and there was good work from the 60s by Olver, but it wasn't fully explicit. The constants were not made explicit, or sometimes there were series that did not converge, they were not said to converge, they converged in the sense of Poincaré and so on. But we need we don't necessarily need optimal developments, but we need fully explicit estimates. So that's what I had to spend a month and a half on. So this is a small contribution to humanity. Now physicists have fully explicit estimates for parabolic cylinder functions. I'm sure they will go and improve them now. So I did this using the saddle point method. So already the fact that this works out in this way qualitatively, you can figure out using the stationary phase method. But the stationary phase method gives polynomial size error terms, which were too large for my purposes. So I had to go use the saddle point method, which in the South American context gets explained very easily, because say that you have a mountain range here, and that you are here, and my flight was from here, and I wanted to integrate a function. And so if I want to integrate a function on some path, and the function is holomorphic, then I can change the path of integration. So what do? I just choose, I don't try to look for the lowest point in the plane, I just look for the lowest mountain path. Now, so a mountain path, what is a mountain path? It will be a local extremum, but in two directions. It will be a maximum on my path, but it will be a minimum on the orthogonal direction. And so the derivative of the holomorphic function will be 0 there. And you traverse it using the path of steepest descent. All right. This is actually one of those explanations that looks fake, but is it real? I think it should be obvious what the endpoint of the integration is, but I think I drew it a bit too far south. Well, what you get is that for the Gaussian, indeed, the transform behaves exponentially for delta small, and it behaves much better than exponentially for delta large. And that's important because that's much more sensitive, because there's 2 pi delta in the denominator. And e to the minus 1/2 h squared is e to the minus 32, which is tiny, really, really tiny. And you have no longer anything to worry about. Very well. So that way you can get estimates not just for the Gaussian as the weight, but for any weight of the form band-limited function times the Gaussian. A band-limited function is just a function defined as the inverse Mellin transform or as the Fourier transform of something compactly supported. Band-limited, again, is a term that comes from physics and engineering. So the only problem with this approach, so this approach gives you very accurate estimates, extremely precise, even more precise than what we need. There is only a small problem. The problem is that it's all based on these finite verifications of the Riemann hypothesis. And by the fact that they are finite, they work only for Q bounded, for a bounded number of characters, that is for bounded conductor Q, and also they work only for delta bounded. Because remember, we have to verify things up to a height of about 50 times delta, if we want the exponent to be 8, or 32 now. So this means that we can give very precise major arc estimates, but only for really narrow, a bounded number of really narrow major arcs. All the rest of the circle must be minor arcs. These are minor arc estimates must be really potent. So a writer for Science was comparing these to Swiss cheese that became Münster cheese. So the holes got a lot smaller, so you have to be much better at eating cheese, I guess. So, well, let's get into the cheese part of the argument then. But let me first give a little bit of a proviso. I was saying f convolution f convolution f, but in fact nobody's forcing us to take one function. We can take 3 functions or just 2 functions, say. And that turns out to be quite nice. So how do you bound, by the way, the cheese, the minor arcs? So like before, we will be bounding the value of the function of the minor arcs, but then what do we do with that? In the case of the major arcs, we just can take the cube and integrate in some clever way. In the minor arcs, that's not nearly good enough. But, however, the trivial approach of taking just bounding that cube, that integral of the cube, by the L2 norm times the maximum, the L infinity norm, and then bounding the L2 norm by Plancherel, that almost works. And that's what has been done always so far. The L2 norm is x log x. The problem is just the log x there. As we will see from now on, we cannot afford to lose a single loss of log, precisely because our holes are so small. We lose a single log in the minor arcs, we are dead. All our logs must be log q, and it's even better if the log q isn't there. So we have to replace that log x by a log q somehow. But how do you do that? There is one way to do that, essentially, by partial summation, so that you are really bounding not the integral of the L2 norm over the minor arcs, because that really is x log x, or x log x minus a constant. You're bounding, rather, MAB, where these are the arcs of the denominator, or B1, B2, where these are the arcs of the denominator between B1 and B2. No? So it all reduces to the problem of bounding that. And that you can show is roughly x log, or you expect this to be about x of log B2 minus log B1. The problem is to prove it, because here you can no longer use L functions. You're in the minor arcs. You're not allowed to use L functions because the denominators are too big. So Heath-Brown already had a technique based on Montgomery's lemma that gives you that result, but with a nasty factor, e to the gamma. In fact, to be completely honest, Heath-Brown gives something that is a bit worse than that. It gives 2e gamma, and then here what you have is log q times log x over log x over q squared. No, so that's what I was working with at the beginning. But then it became clear that even though these two things, so the two you are not going to be able to get rid of, even though it's not there in reality, that's due to the parity problem. The two is very hard to kill. I don't think it will be killable anytime soon. It's a parity problem in sieve theory, but this factor has no right to live and must be killed. And there's a way to kill it, in fact, because this problem is very closely related to the problem of the large sieve. In general, if there's a moral that you must all remember from this talk, it's that the large sieve and the circle method are really two sides of the same coin. And you must not use one of the two as a black box. You must trade ideas back and forth between the two. And that's also how I actually avoided using small sieves during the entire result. You will not find any small sieve except for the trivial sieve. You will just find the large sieve either as such or really eaten up by the circle method in some way, as here. Because what happens is that there was a better version of the large sieve for prime support due to Ramarez, but it wasn't fully explicit. So I had to go and make Ramarez's result explicit for the large sieve. And then that explicit version of the Ramarez's result, I translated back to the context of the circle method. And that's how you get just a factor of 2. That's how those two factors there die. E to the gamma dies, log x over q squared dies. Also, you have to give some shape to your weight functions, globally speaking. So you have these weight functions 8 plus and 8 star. And what happens is that the main term will be proportional to that, whereas that double integral, whereas the main error terms, no matter how good you get, will be proportional to eta plus squared times eta star infinity. So you have to give this thing some shape. And it's best for eta plus to be symmetric, or very close to symmetric, around 1, and essentially supported on 0,2 and vanishing to higher order at 0 and 2. But we already had a requirement on eta plus, namely that it be a band-limited function times the Gaussian, centered on the origin. But that's possible. You can choose a band-limited function so as to get a very good approximation to a function that is essentially a modification of a displaced Gaussian. So that's not particularly hard. That's it. You use G to be a band-limited approximation to the exponential from k to the 2. Also, how would you choose the other weight, eta star? So here there is, if you wish, a political problem, because say that you are the major arcs party and you are the minor arcs party. You have different needs, or if you prefer, the Hardy-Littlewood party and the Vinogradov party. So the Hardy-Littlewood party wants something whose Melling transform decays very rapidly, something based on the Gaussian, for example. But on the minor arcs, you really prefer a nice, simple function, like Vinogradov's, say. If it's even better if it has support bounded away from 0 for technical reasons. It really should have compact support. Tau here uses something slightly more complicated than Vinogradov. Tau uses a multiplicative convolution of just the characteristic function of the interval with itself. No? So it would be nice to use Tau's function, in fact. You will actually prefer Tau's function for comparison purposes. No, it's not optimal in any sense, but it's really quite simple. So how are we going to reach a compromise? Your demands are non-negotiable, really, because this function, Vinogradov's or Tau's, has horrible decay. But your side also has something to say. So there's one easy way, turns out, to combine the two things. Just take the Melling convolution, the multiplicative convolution of the demands of both sides. And then what happens? If you know, if there's are two functions f and g, and you know how to estimate the exponential sum SF of alpha for some alphas, and for all other alphas, you know how to estimate SG of alpha, then you know how to estimate S of F convolution G for all alphas. It's that simple, really. No, I could do it on the board. It's basically just changing the order of integration and summation. Say that you have an alpha for which you know the exponential sum over G, then this is just going to be something of this form. And then you're going to have that you can take the integral fx out here, and you end up, so g is eta blah blah blah, and you're going to end up with an exponential sum over here, which you are going to be able to estimate. So it's fine. But if instead alpha is such that you know the exponential sums over f, then you just use the fact that f star g is g star f. So you can do it the other way around. It's really that simple. So we choose a weight that is a multiplicative convolution of the weight that the minor arcs want and a weight that the major arcs want. And some of you might say, well, we want the things to be at least concentrated away from 0, and that's why you choose eta 0 to be, in fact, t squared times e to the minus t squared over 2. Very well. So what's the new bound for the minor arc? So I put up a new version last year, but I have improved it since then. So it tells you for Tau's weight, in fact, though it doesn't matter that much, as I will explain, that say that you have x not too small, alpha, or in fact 2 alpha, equal to a over q plus an error, and you want an estimate that goes to 0 as q goes to infinity. And you want it to be essentially log-free, as in no log x's in your main terms. So I get, in fact, that an estimate of the quality of essentially, look at the parts in blue. The other parts are much smaller, always. So what do we have there? R looks scary, but in fact, actually, that R has been, I should replace that R with a newer R. Forget about that. But R is bounded by a constant less than 1. It's just that I let it have a dependence so as to optimize things. So you essentially have log delta 0 of q divided by square root of delta 0 phi of q. How large is that? First of all, what is that delta 0 doing there? Delta 0 helps, it doesn't hurt. Delta 0 is never less, delta 0, the larger it gets, the better the bound is, because it's present much more strongly in the denominator than in the numerator. It's present under a square root, not inside a log. And delta 0 is never less than 2, and when delta gets bigger than 8, delta 0 is delta over 4, so it goes on growing, and the bound gets better and better. That's a characteristic of this result that is new. As delta gets bigger, the result gets better. And essentially, the result is then of the type a small constant, less than 1, times log of q divided by square root of phi of q. Very well. And for larger q, you get a bound that is much smaller than x. And as I was saying, r is smaller than a constant. So let us compare this result in the case that is actually worst for this result. So this is a comparison with Tau's bounds. And just remember that the computations will be more than cubic on how good your bounds are. So if something is better than something by a bit under an order of magnitude, then the computation has been cut down by a factor of about 1,000. Very well. Of course, these are just the savings given by the minor arcs. Other parts, such as what I said about partial sums or the factor e to the gamma, those make things better. Still? So we need to do a bit better. We need a bound that is a bit better than 1 over 2 log q to win, meaning that you need to, the computation, you need a major arcs to go up to about 1.5 times 10 to the 5. And that's in fact less than what I told Platt to compute. So it's important in these sort of things to build like a Roman. So people think that the Romans really knew how to build because their things still last sometimes, but in fact that just means that they were over-calculating to be on the safe side. So let us be Romans for a little while, just in case. So what are the main ideas of these new bounds of the minor arcs? So let me just sketch the main ideas. So you really have to aim for qualitative improvements all across the board, in part because if you don't kill all the logs, you're dead, and in part because if you aim for improving constants, you're never going to get done. Improving constants is something you leave for the very end. So you need to do several things. So there's cancellation within Vaughan's identity. We'll go over that again in a second. There's the fact that, as I said, delta, the error, turns out to be a friend, not an enemy, in several ways. So there's the fact that it will be the argument to a Fourier transform, but there will also be the fact that it will force us, it will force two approximations at least to exist. There's, as I was saying over and over again, the relation between the large sieve and the circle method. And there are also the benefits, lastly, of a continuous eta. This is old news, as in, I think many of us already as students had it hammered in our heads, always smooth, always smooth, always smooth. I don't think it's completely true. I think sometimes, as in for Vinogradov's estimates, you do quite well smoothing only a little bit, or as Vinogradov did, not smoothing at all. But rather you should choose smoothings that are appropriate for the context. And then you must develop tricks, as I had to do, to combine different smoothings required by different parts of the problem. So, if anything, the moral should be to each person his or her own smoothing. So what is Vaughan's identity? It's an identity that was developed by Vaughan and also by Gallagher in the 70s in order to simplify Vinogradov's proof. So it's just this. These funny less than subscripts are just truncations. These are Dirichlet, that is multiplicative convolutions in the integers. And these give rise to three types of sums. Well, really two types, type 1, and type 2. Well, what does that all mean? First of all, Vaughan's identity should be seen as some sort of gambit. What do I mean? I mean that you gain a lot of flexibility, that you choose these two parameters, u and v, however you wish. But you do lose something, because if you take a sum for the variable n going from 1 up to x, and you take the trivial bound for the thing on the left, without any cancellation whatsoever on the exponential, then you get a bound of size x by the prime number theorem. But if you apply the trivial bound to the right without trying to get any cancellation, then you're going to get a bound of size x times log x squared. So the trivial bound just got worse by a factor of log x squared. This means that because we cannot afford a single loss of logs, we have to let those logs be created and then kill them all, or at least transform one of them into a log q and then kill all the other ones. The alternative would have been to use a log-free formula, such as one of Vinogradov's choices later in his life, also the Boussier-Rivas, but that gives rise to other complications. So I started with that approach, in fact, but then I went back to Bond's identity. And I must also say that you must kill more logs than you can imagine, because close to the beginning you have to use Cauchy-Bunyakovsky-Schwarz, which is really just Cauchy, but never mind that. And so it's like an axe, right? So you hit a problem with an axe, and then but if it's a hydra, then it splits into two smaller hydras, two logs. The log just got squared. So you have to kill both of the two logs separately, in different ways, as it happens. So how do you kill logs? One thing is there are some, in type 1 sums, one of the things that you don't find in tau, but that can be done, is just get cancellation in mu of n over n. This looks trivial until you realize there's a congruence relation down there, but it's an easy congruence relation. It's d divides n. So all you need for that is, you don't need L functions, which you're not allowed to use in the minor arcs. You just need a zeta function. Or there are even elementary bounds, granular gamma ray, that let you save a factor of log. And then there are other bounds that let you save a factor of log squared. So it's also the case that Vinogradov's basic lemmas can be improved. Already the Boussier and Rivas improved them numerically. But you can also give some qualitative improvements. And once you have the input from a smooth weight, then you can improve them further. One of the harder parts is getting cancellation again on mu in this funny sort of sum, where the ranges are really quite tight. And again, remember, you're allowed to use the zeta function, but no L functions. And you also save another factor of log using the fact that when you have the large sieve and your sequence has support on the primes, then you can save a factor of log. And this is already well understood, and there are several techniques for that, using just a large sieve without going through small sieves. So I was speaking of our friend delta of x. So first of all, is the input, it's the argument of eta hat, and since our eta is even in the case of the minor arcs continuous, you're going to have that, and in fact its second derivative is integrable, you're going to have that its Fourier transform has at least quadratic decay. But you also have the following. So just the simplest result in the Feinstein approximation, just proven just by Dirichlet by pigeonhole, tells you that every real number has excellent Diophantine approximation. So if delta is not very small, if it's small but not very small, then it means that your approximation A over Q to alpha is good but not excellent. Hence, there must be another approximation, A prime over Q prime, which is also quite good, which is actually much more accurate, and for which Q prime could be much larger, but it's not larger than X over a constant, say. So it's also useful. So you are going to be able to alternate between using A over Q and using A prime over Q prime. Both of them are useful approximations. They are not successive approximants in the sense of continued fractions now. They are simply two approximations that are defined and distinct because delta is not too small. The other thing is that when delta is small, the input to the large sieve gets scattered. What is a large sieve, really? So it's an approximate Plancherel identity. So Plancherel tells you that f hat is just the L norm over the integers. So Plancherel tells you that the L norm of the L2 norm of the Fourier transform is the L2 norm of the function. Now you can ask yourself, well, what happens if I don't have all the points in the circle? What happens if I just want a sample of points in the circle, right? Where these points have a very soft, well distribution requirement, namely they are separated by at least delta. What about it? Well, then the large sieve tells you that, of course, you're not going to have an identity, but you can still have an inequality of the right strength. This is the large sieve that I have been talking about. But what are these points alpha I? Well, they are essentially multiples of alpha in our case. And what happens to multiples of alpha? If alpha is just A over Q, then the multiples of alpha are just 1 over q, 2 over q, 3 over q, in a different order, but it doesn't matter, up to q minus 1 over q. So you just input all of those results and you give it to the large sieve. So in that case, you have that delta is 1 over q, and you just give q points to the large sieve, and that gets bounded. And that's very nice, except that you have to do it again and again every q steps. You have to divide your sum into chunks of length q, and give each one to the large sieve. So your final bound from the large sieve gets multiplied by the number of chunks. That is the length of your sum divided by q. Now, if delta is not so small, then when you go around the circle, why are the points not evenly spaced? Not because I'm terrible with Xfig, but rather because I was doing that on purpose. Look, the delta causes it to be a bit bigger than 1 over q, here, here, here. So here, you get a bit closer than you should to the origin. So if you go once over, you're not landing on 0. You're landing at delta q over x, right? For simplicity here, I'm assuming a equals 1, but it doesn't matter at all. So here, you're landing at delta q over x. You have a small displacement, and so on and so on. But that's good, because that means that it's like film that you overexpose time and again. You can go several times around the circle, and the points are not going to be too close together. Delta is going to be positive. It's going to be delta q over x instead of being 1 over q. Delta q over x is smaller than 1 over q, but it's not so tiny. It's in fact quite useful. And at any rate, the dependence on delta here is not that strong. So it turns out that you have to call the large sieve many fewer times. Essentially, you have to divide your sequence into, in this case, it will be just as many chunks. The chunks can go for as long as the green points don't conflict with the blue points. So you go green, you choose another color, and then only once you move very close to here, must you stop and give the entire set of points to the large sieve. Only then. So as a result, you get a total bound of order x over delta q instead of a bound of size x over q. All right, so all of this works out very nicely, starting at about n equal to 10 to the 29. Or in fact, long beforehand, if you want your proof to be a bit longer, and if you are ready to build a bit less than a Roman, if you want to leave yourself less elbow room. It can easily work starting at 10 to the 27, or even starting at 10 to the 25, say. Then the most expensive computation suffers a little. So all of these, of course, things start at a certain integer because you get an expression of the form main term plus error term. The error term goes to 0 as n goes to infinity. We want the error term to be smaller than the main term, and that starts happening at a certain n. So 10 to the 29 is fine because we have already seen that we have checked things up to 10 to the 29. In fact, 88 times further than that. So everything's covered now, and now we have that every odd number is a sum of 3 primes. And that's it.